Hey everybody, how's it going? Today I want to show you that if n and x are whole numbers with n not equal to 0, then the nth root of x must also be a whole number or irrational. So what do I mean by that? Well, for example, we know that the square root of a perfect square is just a whole number, right? But what if I took the cube root or, a different root of that same perfect square? Well, you might be asking yourself, hey, maybe this is equal to something like, I don't know, 1/4 or like 1/3 or maybe 1/17. Well, I'm here to tell you today that that's not possible. I'm here to show you that if it's not a whole number, then it must be irrational necessarily, right? It even works for things like the fifth root of 17, that this necessarily is an irrational number and not a rational non-integer. So let's prove that now. Proof. Suppose suppose that the nth root of x is a rational number that's not an integer or a whole number. So we'll say with p and q whole numbers with q not equal to 0. All right, well, there are two possibilities here. Case 1, q equals 1. Well, this implies that the nth root of x is equal to p, which is a whole number. Great, so that's one possibility we checked. See? All right, well, how do we know it's not a non-integer rational? Let's see. Let's look at case 2. Q is not equal to 1. Okay, so we'll observe that that x has to be equal to p to the nth power over q to the nth. I just raised both sides of this to the nth power to obtain this result down here. Okay, let's multiply by q to the n on each side and isolate p to the n. So this implies that q to the n times x must equal p to the n. Okay, where to proceed from here? Well, since q isn't equal to 1, we know that by the fundamental theorem of arithmetic that there exists, we'll say, prime number g. So there exists a g in the set of prime numbers such that g divides q. Okay, great. Well, this implies that g also divides q to the n. Because think about it. If you have q to the n, and we know that there exists a k in n such that q to the n equals g times k, well, this is the same thing as saying that, hey, this q to the n, you can just multiply it to itself n times, right? This is equal to g times k. Okay, well, let's divide each side by g over g. So we know that if k really is, a natural number or even a whole number, we could say, actually, yeah, then g has to divide one of these q's, right? And if q truly is the same number, if it divides one of them, then we know that it also divides all of them. So moral of the story, if g divides q, then necessarily it divides q to the n. Let's proceed with the proof. Just got to erase all this. Okay. Well, if g divides q to the n, then by Euclid's lemma, we know that if a prime number divides the product of two integers, which is p to the n. Actually, let me write that down. We also know that if g divides this stuff, then it divides p to the n, because p to the n is made up of these factors here. And again, by Euclid's lemma, if g divides p to the n, the product of integers, then it must also divide p itself. Also, I should have stated up here that the greatest common divisor of p and q is equal to 1. Let's also suppose that that's the case, that this is a fully reduced fraction here. Sorry, I should have said that earlier. Okay, so we have that g divides q and g divides p, which implies that the greatest common divisor of q and p is not equal to 1, which was our initial assumption. So this is a contradiction. Okay, so we just showed that if the nth root of x is rational, it has to be a whole number. So we have that guarantee. But how do we know that it can be irrational? We didn't prove that there exists an irrational number that equals the nth root of x. We just showed that it cannot be a non-integer rational. Okay, well, let's just chalk up some examples. So we know that the square root of 5, the cube root of 10, and the fourth root of 17, just to name a few, are irrational. By the theorem we just showed here, we just showed that it's impossible. If you can't express this as the to the nth power of, it has to match the index of what you're doing it to, or else it's not going to be a whole number. Then it's going to be irrational. Okay, well, there's our existence right there. So, therefore, the nth root of x has to be either a whole number or irrational. And that's how you express irrationality. It's r without the rationals. The real numbers without the rationals, you're left with nothing but the irrationals. So that's our proof. I thought it was pretty mind-blowing, when I first learned this. And it's even more powerful than just proving something like the square root of 2 is not rational. Because what we just showed here takes care of the square root of 2, but anything like the nth root of k to the n, actually we'll say to the q, where q is not equal. Actually, I don't want to overcomplicate it, but anyway, this is more powerful because it applies. If you can't express your whole number as a number to the nth power, assuming your index is n, that result's going to be irrational. I hope you enjoy this video and have a great day.